So we're going to talk about various devices that we may encounter out in the chemical industry world or in the engineering world in general, where thermodynamics is important for these devices, especially because they involve materials that are flowing through these devices and their energies are changing as they flow. So let me just quickly remind you of the energy balance equations that we'll be dealing with when we have a flowing material. This is the basic equation for a flowing stream where we have the change in enthalpy is equal to any sort of heat or work done on or by the system. And let's look at some devices where this is important. So the first device I'm going to talk about is a heat exchanger. And heat, as the name implies, is designed to exchange heat. Let's just start out with an example here where we have a pipe here. So I have drawn a pipe here and we have some fluid flowing through it. It could be water, it could be methanol, it doesn't really matter. It's just some fluid, some liquid that's flowing through this pipe. And it comes in at a temperature of T1 and leaves at a temperature T2. Because there's this temperature change between the inlet and the outlet, that means there's an energy change where the enthalpy of this particular pipe or of this fluid is changing. Now, in this case, there's no work being done on the fluid. It's just flowing through the pipe, so there's no work going on. So the only way that we can have any sort of change in enthalpy is through some heat term. So in this case, what we have is heat taking place. Assuming the case that T2 is greater than T1, then the equation is delta H is equal to Q. So in this case, we're just adding in heat and it's heating the system up. Now, in this case, if we have this pipe, if we were to couple it with another pipe, let me just be clear here. T2 is greater than T1, so we're adding in heat. Let me draw in another pipe. So what I've gone ahead and what I've done is drawn a second pipe where there's some heat being exchanged between the two. Again, this is the heat exchanger. So what happens is there's some fluid at temperature T3 and it gives up some heat and comes at a lower temperature T4. Because it's cooling, it's giving up energy. And that energy it gives up is how much heat is coming off. And if we put a hot pipe or a hot fluid and a cold fluid together, what will happen is the hot fluid will heat up the cold fluid, and that's exactly what a heat exchanger is designed to do. It's exchanging heat between two fluids, whether those are two liquids or two vapors or whatnot. And the underlying equation is simply delta H equals Q. And in this case, the change in enthalpy for both streams, if we're assuming this is 100% efficient and we're not losing any heat or we're not having any leakages or whatever, any enthalpy change for this fluid is the same as the enthalpy change for this fluid. So all of this enthalpy that we lose by going from a hot temperature to a low temperature comes in the form of heat, and that heat comes over to this fluid and heats it up, and all of that heat goes up to rise the temperature of this second fluid. So we can use these equations here to calculate how much heat is giving off. And again, delta H will be the same for both fluids because the heat is coming from one pipe to the other. The only subtle difference is that the delta H, the enthalpy change, will be the difference, but one will be positive, one will be negative. In this case, since we're lowering the temperature, the enthalpy change is negative, but since we're raising the temperature for this one, the enthalpy change is positive. And that's the idea behind a heat exchanger. The only thing that's happening is we're having heat being either taken from a system or added to a system to heat up or cool down a fluid, whether that's a liquid, vapor, or whatnot. And that's the heat exchanger. So this is the basic turbine. A turbine is a device that is designed simply to produce work. And what happens is you have a stream of a high pressure, high temperature fluid. Oftentimes we use steam, so in real working turbines in most chemical plants or electrical plants or working plants, we use steam, and it's at high pressure, high temperature, and it comes through a turbine, and what it does is it spins the turbine. And that's because this high pressure, high temperature steam has some kinetic energy due to its high temperature and high pressure, and it spins the turbine as it pushes against blades. And that spinning motion, what it does is it creates electricity. So if you remember back to your basics of electricity generation from your physics courses, you can spin magnets to generate electricity, and that's exactly what a turbine does, is it spins this turbine creating electricity, and the outlet is a low temperature, low pressure stream coming out of the turbine. So T2 is less than T1, P2 is less than P1. If we design our turbine sufficiently well, we can minimize heat losses. So in this case, Q is approximately 0, so we're not heating up the surrounding atmosphere or anything else. So the energy balance equation is the one shown here, where we only have a delta H and we only have a work term, and so that the work that's produced by the turbine is simply equal to delta H, which we often quantify as just m dot times the specific heats of the outlet versus the inlet. And so this is the basic equation here. Remind you, if work here is negative, which it should be for a turbine, that means that work is being produced by this fluid on the surroundings, and that's what a turbine does, is it gives up work. It produces energy for the surroundings in the form of work. So the other piece of equipment that we deal with a lot is a compressor. And a compressor is essentially the opposite of a turbine. A turbine is designed to produce work. We have this high pressure, high temperature stream coming in, and that goes through the turbine and produces work. Well, a compressor does the opposite. We actually consume work. We're adding in work. So we actually are spinning it. So we put in some work into the compressor, which spins it. And what it does is it compresses the outlet fluid so that this stream 2 coming out of this compressors comes in as stream 1, then comes out as stream 2. It has a higher pressure. So we oftentimes, what we want to do is if we want to increase the pressure of some stream, whether it's a liquid or a gas, or predominantly gas, if we want to increase the pressure, we will go ahead and put it through a compressor. And to increase the pressure, we have to put in work. And this is just this energy balance equation. Again, we're ignoring any heat. We assume that there's no heat coming out of this compressor, but all of the work coming in is it's changing the enthalpy from the outlet to the inlet here, and that's manifested by the change in temperature and pressure on the compressor. Let me just add one little part to this. Compressors are usually used for gases. That's the typical inlet that we put through a compressor, some gas or a vapor stream. On the other hand, a pump is designed to move liquids, and the idea is simply the same, where we have a liquid coming in and then leaving it, and then we're putting work through it, and we're changing the enthalpy of the inlet to the outlet from a pump, but in this case, just the stream flowing through is a liquid, and that's the case for a pump. So next I just want to talk about a valve, and a valve is simply a device that is usually used to constrict the flow of a fluid through a pipe. And when it does that, what we often have is a pressure drop through that constriction. So it's a way to control the pressure. So if we have something at high pressure and we go ahead and put a valve on our system, we can get the outlet to this valve something that's low temperature. So high pressure comes in, low pressure comes out. So a valve is essentially a very simple device. The heat losses, if it's designed properly, are 0. So in other words, heat is 0. No moving parts really to speak of, so work is 0. Kinetic energy changes are usually negligible. Potential energy changes negligible. So if you just use the energy balance equation, then delta H is 0, implying that the enthalpy coming into the valve is essentially the same as the enthalpy going out of the valve. And so working with the energy balance is pretty simple because of this case. We just have enthalpy going in equals enthalpy going out. Let's mention one other device, and that's a nozzle. And a nozzle is something I think you're probably all familiar with. If you've ever gone out to your yard and you found your garden hose and you hooked on one of those little nozzles on the end of it, and when you turn on the water coming out of your hose through the nozzle comes out at a very high velocity, and you can, spray people and spray bushes or clean cars or whatever you want to do with it. And the idea behind a nozzle is that we control or change or control the kinetic energy of the fluid coming out of the end of the nozzle. And so in the case of a nozzle, delta kinetic energy is not equal to 0. On the other hand, work is 0, no moving parts, heat 0, potential energy usually 0. So if we do our material balance, we get this equation right here. And so it just tells us that we can control the velocity of a fluid moving through our piping system, or whatever system we have, just by use of a nozzle, just like shown here. Now let me just say one other thing here. All of the different devices that I've shown you here involve energy balance equations. And again, to find out, how much heat we put into a heat exchanger, or how much work we're producing from a turbine, or whatever, we need to know the changes of enthalpies. And this is where, again, using the steam tables, or even sometimes integrating heat capacity parameters or so forth, we can use those to calculate changes of enthalpy, and in turn calculate how much work is being done by a turbine, or calculating how much work we need to put into a compressor, or calculate how much heat we need to put into this heat exchanger in order to heat up a certain fluid. But we'll use all these equations that I've illustrated here in order to study and work with fluids going through these different process units.